All right. Good morning, good afternoon, good evening to everyone. Probably a smaller group than we initially had planned for, as we ran out on the first link that we had sent out to everyone. So apologies for that. Obviously, we will be sharing the recording of this with all of you post the webinar. And we'll be certainly doing additional sessions later on in the coming weeks and months, which will certainly go to plan. So just a quick introduction. So from my side, I'm yours. I'm leading Diabatix now. Very happy to be part of the Diabatix story. It's the anniversary year for Diabatix. Now 10 years in the making. And yeah, we're really planning on a lot of, I would say, new stuff, new developments, and new people to the team coming. So you can expect a lot from us in the near and midterm future. And beside me is Adam.
Yeah, thank you, Yuris. So my name is Adam. I am a member of the application engineering team, and I will be providing support to clients with the setup of the cases, and I will walk you through in a bit of time through the workflow we have prepared for this webinar.
Thanks. So today is actually a follow-up session of the semi-therm workshop that we did in San Jose a few weeks ago. So for those of you that were there, I promised you that we would indeed have a bit of a deep dive on the actual workflow that came up with the case that I presented. So that's the objective of today. But before we do that, I'm just going to go through a few kind of background input in terms of how we got to that particular case. So as an agenda for today, we'll look at obviously, what the problem statement is, and what the challenges are, and what's driving kind of thermal management change, and that's obviously the background and the key focus of Diabatix. And then we'll go into, I would say, the solution itself. The solution is ColdStream, and how ColdStream is tackling where these traditional cooling techniques are hitting their limits. From there, we'll go into a brief overview of a GPU cooler case. That's the same case that I showed at Semi-Therm. And then Adam will take us through that entire workflow from all the way beginning, importing the geometry to the fully optimized case, and show effectively comparisons of the different designs that we came up with. And basically, also during the webinar, feel free to post your questions in the chat. We'll have normally some time at the end of the webinar to tackle those questions. So feel free to start plugging them in. So I would say from an overall thermal management challenge perspective, there's obviously a number of key elements that come into play. Most of them, I think, are well known to all of you. When we look at, long engineering cycles, obviously simulations and CAE tools have been there now for a while, and they obviously help in reducing these engineering cycles. But still today, those are highly manual, and again, I think that's a key focus for us to be able to address. Drive those engineering cycles down in terms of time. Another key element is obviously, I would say, the manufacturing of these thermal solutions themselves, right? So obviously there's, over the last number of years, there's been quite an evolution in terms of new manufacturing techniques coming into play, which now also offer a high scalability to go to market and drive some new insights and designs. And last but not least, there is obviously a far increased, let's say, challenge in terms of tackling these increased power density applications, whether it's in the data center, whether it's in automotive, whether it's in aerospace and defense. These challenges are broad and cross-sector. So I want to double click a bit on that last point. So if we go to the next slide, this is, I would say, with a key focus on data centers, and that's kind of the main topic of today's webinar. Obviously the the demand for GPUs has really skyrocketed, right, over the last few years, and they've been driven by the rollout of AI factories, right? So we obviously all know the let's say the coming of the large language models and etc. So that has really, I mean, driven a massive demand for the rollout of GPUs in these AI factories. And so with AI factories and GPUs, the key is to be able to run inference using AI tokens. And the key is that when we think about a data center, I mean, let's say a 1 gigawatt data center will have a cost of around $40 billion over a 5-year amortization plan. And that's actually without the equipment in it. And so when we look at the graph on the right-hand side, this actually shows the amount of tokens that we want to be able to use versus the complexity of the inference or the complexity of the problem that we want to tackle. And for those of you that saw, I mean, Jensen Huang's GTC keynotes a few weeks ago, he basically refers to that as basically the throughput of the AI versus the smartness of the AI for a given power, for a given watt. So actually the objective is to be able to move that curve upwards, right? So for the same power, you'll get, so for the same indeed power input or watts, you'll get more AI power back. And that drives the revenue of the data center. But that obviously means, if we go to the next slide, that we need higher power or higher density equipment in those data centers. And that's what we see basically on the right-hand side in the curve. You see the evolution of the GPU power over the last years. And so, I mean, when we look at current date, 2025, 2026, I would say the best performing GPUs are more or less around the 1 kilowatt range. But the expectations is certainly that 1 kilowatt will increase to 2, 3, and probably beyond. And that's where obviously the traditional cooling technology and techniques, whether even it's direct liquid cool to chip and immersion cooling, that's where we need to look at driving new designs and new innovation to be able to tackle those thermal challenges, because with today's techniques that will no longer be possible. So with that, I wanted to take you through a very brief kind of outlook and background of ColdStream. So if we kind of look at the next slide. So the background of ColdStream really is to allow and enable engineers to drive designs beyond the realms of what traditional methods can bring, right? And so really bring designs beyond, let's say, the manual sequential techniques that are used today, and bring new insights and novel ways of thinking using a smart approach. And so if we go to the next slide, ColdStream in itself is a SaaS-based solution. You see some of the interfaces here, which you will also see in Adam's workflow presentation. And so it's a SaaS solution which basically allows to run and drive any kind of thermal problem, whether it's air cooled, liquid cooled, natural convection, forced convection. I mean, you name it, we can tackle it. And there's been a very strong focus on productivity for engineers. And so it's a workflow which is extremely streamlined from input to output. And so that's really what we wanted to show today. Just as a kind of a quick note, this is the approach from a building block perspective behind ColdStream. So what we do, and again, I'm not going to speak too much about this because you'll see that in the workflow. Obviously, the background or the core of ColdStream is the connection between the simulation engine, which can run from 1D to full-blown 3D CFD. That's connected to a generative design engine, which basically updates the design via smart algorithms. And the key is that those two pieces are intrinsically connected to, obviously, material basis for the liquids and solids, and as well the manufacturing technique behind, to make sure that the designs that we create with this innovative thermal design approach are actually. And then one thing that I haven't mentioned, which is the shape generator, which you see here. So we've actually built into ColdStream a number of what we call standard design templates. You see them here: pins, fins, but also a number of TPMS type structures like leadinoids, gyroids, and so on. And we typically use that in our workflow as well to be able to, again, drive some of these generative designs in a more optimal way. And so these are some of the elements that we'll see basically in Adam's workflow presentation. And here you see a number of the different types of applications that we do. Again, as I said, we can run any kind of thermal management problem, whether it's air-cooled, liquid-cooled, heat exchangers, battery cold plates. But indeed, here today, we're going to double-click on the CPU, GPU cooler. And so just to kind of lead in before we start with the good stuff for all of you, that's all of what all of you have been waiting for. So the case that we're going to speak about today, and that's the same that I showed during the Semitherm workshop a few weeks back. So it's a GPU cooler case. I mean, you see some of the elements here. Again, it's no surprise. Traditional design is a skived fin approach, which again, with these increased power densities are hitting the limits. So what we've done here is we've run this particular case with a uniform 2 kilowatt heat source. If needed, we can actually run various loads and actually integrate those varying loads within the optimization process if needed. But again, here we've run it as a uniform case with a minimal feature size of 250 microns. And what we want to do is we want to compare the skived fin solution at that resolution with 3D additive manufacturing. Again, as I said, the advancements in 3D additive manufacturing are such that we're now able to start driving into scalable designs using that process. What we were able to do using this approach is basically what you see here. So we ran a number of different, let's say, steps in our workflow, going from the baseline to standard design templates into a custom design. And here you see the split. So the left-hand side shows you the skived fins versus the right-hand side, which is the 3D additive manufacturing, or as we sometimes call them, free form cold plate. And you see that, I mean, at the same resolution, the same input power, we're basically able to drive 10% thermal resistance improvements at a greatly improved thermal uniformity. And so what we're going to do now is Adam is going to take you through full workflow. We're not only going to double click on this particular comparative case here, but we'll actually take you through a number of the different steps that we've done to come up with this comparison. Adam, over to you.
Hello, everyone. My name is Adam, and I will be walking you through the workflow for the setup of our GPU cooling. And we were going to be taking as a reference our case setup with an NVIDIA chip. So we will be going through first base case with skiving fins, and then we will jump to case created with 3D printing, additive manufacturing, and we will close up with a comparison with different mass fluxes for different RPMs in our freeformed design. So once we are inside our generated base case, this one is already completely filled. That's why you see these green arrows and it says that required input is completed. And otherwise you would see a pencil, which would request that some input is still required. You will see that in a few steps. Basically, the geometry is very easy to add. So we just click in the plus button and we just add the required file as a step file. And this can be done by adding the whole compound or just adding separate regions. And the interfaces are automatically generated. But in the case some interface was missing or we want to add an additional interface, it's as easy as select between the regions again and create it in the interface. So walking through the setup, as you can see here, we have half case that we're going to be going through today. We have our housing, which is a solid region type. We can choose between solid and fluid. We will here select the material, which is copper and copper alloy, and we can actually select between one of the available ones that we have here at ColdStream, or we could just create our own material, even with isotropic kappa. Going through the patches here for the boundary conditions, you can see they're created as insulated walls, which is equivalent to the symmetry boundary condition for the solid. And as for the cold plate, we again have the same configuration as for the housing, same mirror patch, and then we have our GPU heated wall. For this boundary type, here we can select between different types of boundary types. We will introduce our physical properties, and as for the targets, we can choose between a variety of targets, whether it's temperature spread minimization, temperature minimization, mean temperature, and so on. Very easily, just by creating and selecting, adding at the target. And here you can see that now we have this incomplete output with the pencil that I was mentioning just earlier. And this weight value, this weight parameter, serves as a weighting factor in case you have multiple targets to just give more importance of one over the other. And just to close, we have our fluid region, which in this case is this one. We have to select, again, this time fluid type, and our material, which is water glycol mixture. We can select, of course, another material. And our turbulence model, which in this time is ceramic SST, and we can choose between a variety of models. For the inlet and outlet patches, we can choose again between a variety of different boundary settings. In this case, it's going to be fixed flow rate inlet, and we're going to just give volumetric flow rate type. We can choose between velocity and mass flow rate again. And we just input the parameters and input the target. In this case, is pressure loss. We could also choose to have pressure loss minimization as an objective. For the outlet, we just select pressure outlet with 0 pascals. And the design region is the design that's going to be of interest for us, which is going to be the design that will be varying its shape. So we're going to go from skiving fins to geometries created with 3D printing additive manufacturing. And if we wanted to start from a design already existing, it's as easy as enabling this slider and uploading the design. But since we're going to use this to create our own skiving fins, we will leave this unselected, and we will be actually ready to generate our design options. And of course, we could here also add our targets. With clicking on generate design options, we have the possibility of creating simulations straight away. So if we wanted to test the baseline geometry, which in this case would be empty, or you can select straight away the standard design, which would be the parametric creation of our geometries. So in this case, since we are on performing skiving fins, here we would select skiving fins, but for 3D printing, as you will see a little bit forward, we'll create 3D printed geometries. The good thing from this configuration is that all of this setup that we generated for this baseline, for this base case, will be translated to the standard design, but minor details that are actually additional features that we need to configure and that we will see shortly. So after just giving it a name, for example, test, I could create the case, and also I could add multiple cases to just do it everything from one click and from one base case. So once we are inside our standard design, where we are going to create our skiving fins, we will see that all our setup is going to be included, but the design options, where here this time we will going to be able to select the manufacturing method and the shape settings. So in this case, we would select skiving with continuous rectangles, and we would include the resolution that we want. So in this case, it's going to be 250 microns. And again, if we wanted to just select different constraints, it's as easy as just selecting it and describing it here and just adding the settings. The manufacturing direction is -Z, basically because we're here on the Z plane. And once this is included, don't forget to add the material, which is also going to be missing. And this will actually be ready to run since the rest of the configuration, as for example, the heated wall, is already included. So this would be ready to submit. But as you can see here, this is already a finished case, correlation based, which means that is the lowest fidelity, because actually we want to only to generate the basic structures. So this is a 1D approach. And from here on, we could very easily just select the best performing design for a full-blown 3D simulation. Once we open the results of our standard design, we will be able to see different windows. So the very first window, by default, is going to open the case summary. But the very first window is the workflow, where we could see the workflow that we're currently running on. But in the case summary, we are going to see a very brief introduction and a summary of the case that we are actually running. The thermal network is not that interesting for us at the moment because it's only the representation of this 1D approach with the graph of the thermal network. But what's most interesting for us here is actually the design evolution, where we will see actually different iterations in this process. And this upper graph will actually show which is the best feasible design, and here with additional targets that have been included. And what we would do here is just select the best performing design, which is iteration 46, which is already selected. We could see some results here if we wanted, but the most important thing would be here to actually verify the design performance, which would be to perform the full 3D CFD simulation, or to improve the design if we actually wanted to jump from standard design to custom design, where we would perform the topology optimization based on our geometry and based on the design selected. So once we have created our skiving fins as a starting geometry, we have to compare it and test it against a 3D printed geometry. So in this case, the base is an empty case, same empty case as with the skiving fins. And to this, we have connected straight away 3 different types of 3D printed geometry, which are gyroids, split P, and double diamonds. And as you can see here, and I will show you just in due time, is that split P is the best performing configuration of all of those. And here we would plug actually a verification of this standard design to see the actual performance of the best iteration. And we will have at the very end our custom design. So in order to show you the difference between our 3D printing manufacturing constraint and the skiving fins, I have selected the split P. And again, all the configuration will be already inputted from our base case, and the difference will rely on the manufacturing method and the shape setting. So in this case, we have selected 3D printing, and the split P, among with the 3D printing ones, we have included again the manufacturing constraints, and as easy as before, we could select between the existing ones or just create a new 3D printing manufacturing constraint. And again, we would select the material, and this would be everything, and we could actually submit it again for standard design. And same as before, this case is already finished, so I will show you straight away the results. So I was mentioning before, workflow will just show you the workflow of the case that I showed just before in a different window. Case summary just includes a very brief summary. Thermal network includes you the 1D approach, and the most interesting part is the design evolution, where we can see here a preview of our geometry created with 3D printing. And you can see here a lot of structures. In this case, as you can see here on the top right, the iteration 95 is highlighted, which is actually the best performing one. And this is the geometry that has been generated with the parameters that we have introduced. So once we have this, we have, again, 2 options, verify the performance with a full-blown 3D simulation, or just improve the design with our topology optimizer, which would give us our freeform geometry. In case we wanted to compare 3 of our standard designs, so the best way would be here on the right side, click on the 3 buttons, and what I will do is remove from comparison first so that you can see. These 2 are already in comparison, which are split P and double diamonds, and what I will do is just add to the comparison this gyro that I just removed. And on the very top of the folder, we can see that here's 3 cases in comparison, and by just clicking here, we are going to be able to see the comparison. Once we're inside this comparison, this is what we're going to see, all 3 standard designs. And it's as easy as just click on select best feasible iteration, and the system will already find which is the best iteration to compare with. And as we're going to see here, and I already briefly introduced before, from gyroids, double diamonds, and split P for our case configuration, the best performing one is actually split P. So this is the one that we will be using for the custom optimization and for the topology optimization. Before jumping straight away to the topology optimization, I wanted to show that those are the results for one of the iterations of split P, where we will be able to see that actually the values of the results and the results itself vary from the results obtained by our correlation method, which is a 1D approach, because this is a full detailed CFD simulation, so this is 3D, and this is quite more accurate than the 1D approach. And this is what we will have to take into account, and those are the results that we will use to compare with further cases. So once we clicked on improve design performance in our standard design of our split P, since we mentioned that's the best 3D printed geometry of the ones that we tested, what we will see is again that all the configuration will already be brought from previous steps. But again, the difference will lie on the design region, where we will see that this time there's an initial design loaded that you can see here. And to allow the visibility, we have to click and click this little cube. But you can see that the geometry of the split P is already loaded. And the difference lies on the methods that we have here and on the degrees of freedom that ColdStream will have. So if we select add and remove material, what the software will do is from this starting geometry, it will be completely free to add and remove material as it wishes to find the best performing structures in our design region so that it optimizes for the targets that have been included at the beginning. Again, if we go to GPU heated wall, we will see that we have for this simulation temperature minimization, and we have at the inlet maximum pressure loss. But going back to the design region, this is for add and remove that I was explaining. We have only remove option from the design that's been introduced, the split P. The software will only be allowed to remove material and to carve out holes and more free-formed areas to allow a major flow flux in those areas. And only add material, which would be the opposite, which would be start to block some of the paths that this geometry has and create blockages so that the flow is redirected in another areas. And the manufacturing settings will have to be reintroduced, and we encourage here to introduce the same manufacturing settings that were introduced in the standard design. So again, 3D printing with a resolution of 250 microns. Since if we introduce a different manufacturing settings and constraints, we can actually end up with slightly different geometries, and this might affect on what we really wanted at the beginning. So it's very important to be consistent here. For some configurations, it might be interesting to change this number, but for this specific case, it's better not to do it. Again, select the material, and once all of this is generated and all of this is configured, we would be able to submit our case. And since we have selected here only remove, what this will generate is a free-form geometry with some of the 3D printed structures being carved out. So instead of running straight away the verification of the geometry that was free-formed, what we did is include that geometry into this base case and compare it with the same geometry but run in different pumping power. So as we can see here, and by the namings of the cases, we have 2 kilowatts everywhere, but we have increased the LPM from 225 to 7.5 and to 12.5 to see what's the difference here. To be able to see this comparison, so once we select our 3 simulations in the same way that we did prior with our standard designs, we'll see straight away this table, which will compare temperature and also other properties that I will show shortly. But as expected, if we increase the pumping power, and again, we're taking this to the absolute limit, not only for the 2 kilowatts on half of the chip, but also with increased pumping power. We can see something that's expected. So when we have higher pumping power, we have better cooling. But actually, with the 15 LPM, we see that it still improves, but not really that much in comparison with the 7.5 LPM. And the reason is that we have very high numbers in terms of pressure. So we have a lot of pressure drop here. But this is also expected because, as I was mentioning, we're testing this to the absolute limit. But what's important here to show it's not actually the number, but that we are able to solve those simulations correctly without being or without becoming fatal crashes. And here we have additional comparisons available as flow rate, heating power. But the one that's actually more relevant is the temperature variance, where we can compare easily the uniformity between cases. And again, this is a very important parameter that we can very easily compare. And having this said, we'll wrap up here this webinar. I hope you enjoyed and see you in the next one.
Great. Thanks, Adam, for this very exhaustive demo. For those that are also still interested to see indeed the comparison of where we showed the 10% gain, we can also send you that comparative sheet. We haven't included it here in the demo, seeing that we wanted to look at various types of elements there, but we can share that if that's of interest. Questions, and just going to pop into the Q&A section here. Wow, okay. Yeah. So we have quite a few here.
Yeah.
Okay, so all right. So one of the questions, there's a few actually which tie together on. So it ties to being able to use different levels of fidelity, and then link to that somehow. What is the best workflow to use ColdStream? I mean, as Adam showed, the workflow that we recommend is really to start from, I would say, the 1D thermal network approach. There's a few questions also that came in about reduced order modeling, so I'm going to speak about that in a minute. So we really recommend starting from a 1D thermal network approach, which is very fast to turn around, and then use that as an input into your standard design, reinforce that with CFD, and then go to full-blown optimization using the CFD solution itself. Obviously, the fidelity, so we can run cases at different levels of fidelity, even within 3D CFD. That depends a bit on, I would say, the resolution of the case. When we think about these cases here for the data center, 250 microns and below, I mean, we're typically running at a very high level of fidelity to be able to capture those small features in the geometry. Reduced order modeling itself within CFD, we do not use yet. There is a number of things that we are investigating in that sense, but more from a convergence acceleration perspective. So that's I would say, a combination of, I would say, a few questions that I saw there. Right, and then I see, then there's one about AI. So how accurate is your AI versus traditional CFD? Okay, that's a really good question. ColdStream is not AI based, so we do not replace the simulations with AI surrogate models, but we run everything at the chosen level of fidelity, whether indeed it's the 1D thermal network or whether it's 3D CFD. So we run every single optimization step of the process with 3D CFD when we think about the generative design. So that's important. I mean, we are looking into using AI for other realms, but we have not yet found the capability of AI to really replace these very, very, very unique one-off designs. Then somehow linked to that, is how does it compare to traditional CFD? Yeah, so it is traditional. So the core of it is traditional CFD. And so there, obviously, we are very much trend capable with respect to other CFD solutions that we know on the market, high fidelity CFD solutions on the market. So that's certainly the case. And then maybe one last one that I can tackle, because I think there's probably a few ones for you as well. Yeah. So how do you make sure that the generated concepts are manufacturable? Yeah, I mean, great question. I mean, that's obviously the key of the solution, and that's what the team has really worked a lot on in terms of integrating the manufacturing process and technique into the optimization cycle. So we make sure that all of the final or optimized geometries that we create are indeed manufacturable. I think you've also seen that in what Adam has showed. In the optimization curve, you had a number of gray points and green points. So it's the green points which are effectively manufacturable. These are then extracted, verified, and then effectively re-related back to let's say the manufacturing techniques which were used to make sure that they are indeed manufacturable. And then maybe as a quick side note, we've obviously run quite an extensive amount of validation cases, not only in let's say the GPU, CPU cooler space, but also outside. We think about battery cold plates and so on, where we've also run obviously simulation, CFD simulation at high level of fidelity, but also experimental work, which we're working with a number of partners, both in process and manufacturing, but also when we think about academia, when we look about some of the use cases that they would be running. So we have a quite an extensive database there.
Yeah, I saw some question regarding like the workflow integration. So yeah, as you saw at the very beginning of my presentation, we are importing the geometries in step file, in a step format. And it's again, I want to just highlight that it's very important that the design region, so the region that you are optimizing for, it's a separate region from the fluid and it overlaps with the fluid. You're going to be uploading all of those parts as a step file. You can do it again all together or in separate step files. And then the output that you will be getting is the step file or STL file of this optimized geometry that you can then plug again back to your geometry. And of course, then you can reuse the geometries as you wish. But as Joris just said, like we have validated our procedures, and we are very sure that our fidelity is good enough that we don't need additional validation on our optimization and on our CFD simulations. Then I have a question regarding the performance, like how is it evaluated or how is this determined? I'm just gonna go very quickly again over it because I already tackled this, but basically it's a weighted function based on the values that you input as targets. So you can give it a certain weighted value, then it will all be solved as a combination of weighted values, and that's the graph that you obtain. But beneath it, you will be able to just evaluate the performance of each of the constraints and each of the targets individually. And whether if it's 3D generative design really, truly, or if it's just a simplification with a 2D representation, well, I must say that depends, of course, on manufacturing settings, that some of them might be basically simplified, let's say, geometry that's somehow out of extruded. So, for example, if we are talking about CNC milling, but in this case, you saw that this 3D additive manufacturing, so it's completely 3D. There's no simplification there. We are just running a full 3D model and then a full 3D simulation. And just let me very quickly see, because I've seen there are some additional questions popping up.
I see one here. Is it similar to Dakota? So Dakota is an optimization framework which can be effectively run on different CAE tools. So it's not similar in the end shot goal as what we've shown here. So I would say the standard designs that we run are deterministic parametric optimization. In that sense, it's similar to what, for example, Dakota and some other optimization framework can do. But the end shot goal, obviously here, especially for this kind of application, is the generative thermal design, which is non-parametric. And so that's very unique in with respect to, again, the typical manual rule based or even using traditional deterministic optimization frameworks.
And I'm seeing here that if we have e-learning materials, this webinar is being recorded, and you will be reaching to this webinar, so you can spend some further time to just go a bit slower through all of the steps. And we do have additional webinars uploaded that you can also reach out to for further information, and of course not only GPU related.
Yeah. So indeed, we have a number of use cases also available on the website. But as I mentioned at the beginning, we'll be running again, I would say, a regular cadence of these type of webinars. So you can certainly look forward to other use cases, but also updates in terms of some of the new functionality that we're bringing to ColdStream and to the thermal engineering spectrum. I think that we probably covered most of them.
Yeah.
I mean, we're obviously already a bit over time, seeing that we started a bit late. So I wanted to thank everyone for joining. I think we'll be also running a bit of a survey poll post the webinar. Feel free to give your feedback. That's very important for us. And yeah, we'll be sharing this material with all of you. And yeah, look forward to seeing you on the next webinar.
Yeah, I hope to see you soon as well. Bye.
Take care.